Today I'll be talking about Titan, and if you know me from social media or just in general, or even not, and you may not know me, but I will tell you this: I am very biased about the solar system, and so I love Titan. And what we're looking at here in this particular, right here on my cover slide, is this was taken by Cassini VIMS, which is visible and mapping imaging from infrared from spectroscopy. And so this was one of my favorite shots of Titan. And so this is Saturn's largest moon, in which Dragonfly, will be going to during this decade. So this is really exciting for me to even be able to talk about Titan. And so this is the work that I did during my senior thesis defense at Johns Hopkins University. I was at Johns Hopkins interning there, and then this is the work that I had brought home to Chicago State. So if we're looking at this image, you can see the little, you see these little dots here. Those are the clouds, and those were the clouds that we were looking at NAC-tober, which I'll be giving a talk about that later on at a different day. And you can also see this peering through the surface and looking at how everything just sediments onto the surface. And so this gives us a really clear view of what's happening there. Although I will warn you guys, Titan, although I love Titan so much, it does not give us what we want to see. And so that's why I'm happy about Dragonfly. So, an introduction about myself, as Antonio said. Again, my name is Ashley. I received my bachelor's in chemistry from Chicago State University. I interned at Harvard, Johns Hopkins, and NASA Goddard. As you heard, I am a Titan and Dragonfly enthusiast, and I'm the founder of Black and Astro, co-founder of Black and Chem, and co-founder of Black and Physics. And I'm also a science communicator. Now, this is one of the most beautiful pictures I have ever seen of Titan. And so, as we're looking at this picture, this shows us a unique atmosphere in which it kind of looks like home, right? It kind of looks like our home, right? And so, we look at Titan, and when we look at Titan, we use it as a model for early Earth. So I'll be talking about early Earth a little bit later on. And we also can use it as a model for exoplanets and other planetary habitability. So Titan is a really good model for that. But however, I will warn you, this will not happen on Titan. This won't happen. I hope not. I really hope not. If you know the reference, you know this is the Avengers. I hope this guy does not show up, because if he does, I don't know about y'all, but I'm leaving. I don't know where I'm going. I'm leaving. Unless these people show up, then I think that'll be cool. But in all seriousness, I'll tell you a little bit more about Titan. It's the second largest moon in our known solar system. NASA recently updated Titan's moons from 60, I think it was at the time, and then they're like, oh, it's 20 more, so it's like 82 moons. So it has a ridiculous amount of 82 moons, and Titan is the largest. It has a really dense atmosphere, and one thing that I found was cool is that if you take two cardboard boxes and put them together and you flap on Titan, you can fly, which is really cool. So I thought that was awesome. And as I said before, it's compared to early Earth and used as a model for exoplanetary atmospheres. Planetary missions through time, and this was before I was here. This was a long time ago. This is the Pioneer 11, which is actually still out there. From what I understand, that it's all the way out. It's still out there in the solar. It's still, I think it's like all the way past the solar system. And so this picture right here showed an early shot of Saturn, and you can actually see Titan right here at the bottom, the little baby dot. And I thought this was really, really cool to like learn a little bit something about his background early on. Then there was Voyager 1. Now, if you can look in this photo, you can see that it has a little, Titan has a glow about it. And there's a thick haze layer being shown here. This also shows that how the haze is completely with a dark hood. And sometimes people may think it also has a dark cloud layer over the North Pole, but its haze is really, 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 really thick, and it can't let us like really look through its atmosphere like we want to. And so that's why I say we kind of get frustrated with Titan. Like, why can't you let us see what's happening? It does not want us to see it. And the beloved Cassini, which I think it ended in 2017, if I'm correct. These were some of the images that were shown during that time. And if you look at it in comparison to the moon, you can see the objects of the center of the picture is basically the size of a man's foot. And so I thought that was really, really cool when I was, again, learning about these different missions through time. And also how similarly Titan's atmosphere is to other places in our solar system. And my beloved dragonfly. So dragonfly, we'll look at its prebiotic chemistry, its habitability, looking at everything that we need to know that can help us within the future. And so this was really, really, really cool that this was happening. I thought that, like, when I first heard about Dragonfly, I initially was like, it's going to get picked. And everybody in my group at the time were like, no. I said, no, it's going to get picked because people want to go to another atmosphere that looks like home. And sure enough, that's what happened. And so Dragonfly will be looking at some of its sand, its rocks, some of its haze layer, going through the haze layer, looking at its composition, which we've been trying to figure out for quite some time. And so these measurements will be so important on how we continuously go forward within solar system chemistry, solar system physics, and within understanding planetary habitability. And so this is the Miller-Urey experiment. When I first learned about the Miller-Urey experiment, I was just like, okay, that sounds cool. So what happened was, I think it was Miller, who was a grad student at the University of Chicago, wanted to know more about, you know, Earth's early origins and its early atmosphere. And so with this being said, this entire experiment is still being used today. And so one of the really, really, really cool things about this experiment is seeing how, if you look at the electrodes, that spark is mimicking thunder. And so in some places it'll mimic rain, and at the bottom where you see the water, yes, that's my cat meowing. And it is more like rain. It is like rain into the sea, like how we have here. And so what happened was it turned brown. And when it turned brown, it gave us amino acids and things of that nature that helped us understand these complex organic molecules that are in early Earth, which are helping us today. And they also like gave us a new field, which is prebiotic chemistry. I think we safe, guys, for my cat. So going into Titan's atmosphere, if you look at this comparison, you can definitely see very, very similarities in Titan's atmosphere and early Earth. You know, the only thing is maybe they have methane and ethane clouds, and we don't have that here, which is which is fine with me. I don't know about you all, but I think that's okay. But Titan also has methane and methane lakes and rivers and seas. And so I think this can help us understand a lot of things very, very clear. And if we're looking at the stratosphere and the troposphere and the tropopause, those things are also key to helping us understand like how it rains, and understanding the haze layer and how the hazes are created. Now, when I look at this picture, I automatically think of when you're in an airplane and you're going over the horizon or whatnot. That's definitely what I think of, and that's what brought me to this picture. But you can definitely see Titan's thick haze layer from what we saw before when it had that bright glow from the Voyager mission. So that was really, really, that was very unique. And looking at it now is giving you a clearer view of what's happening there. All right, the photochemistry. So the photochemistry is really something that it took me some time to learn, but when I learned it, I was so excited. But let me be clear. When we were doing this project and the experiment, and thinking about the Miller-Urey experiment, and then thinking about how we had to set up in the lab, it made so much sense, and it was really, really easy for me to catch on. So I'm hoping everyone else can catch on as well. And so you have the sunlight and you have the energetic particles that collide, and once they collide, then, as you can see in this diagram, they make molecular nitrogen and methane. And so that's when you have photodissociation and ionization happening, which creates organic molecules such as benzene, other amino acids, and they create tholins. And so I'll be getting into tholins just in a bit. And so, this really, really helped us understand how these hydrocarbons and amino acids and produce these haze layers into the surface. And so this also, bringing back to the point of the beginning slide, talking about how things sediment onto the surface, this also helped us understand that a little bit better as well. So now we're going to go a little bit back, but forward a little bit, but you'll get it. So here's Titan's temperature pressure profile at 10 degrees south. And so basically, remember the schematic that I showed you all with, and there she goes, with the schematic with the comparison to early Earth, right? So this is basically what you're looking at. And so this just tells us how far everything is from the surface. And at this point, Cassini-Huygens, the HAZE instrument, was taking note of this. And so this how a lot of us was able to get data from the from that and the CIRRUS and the INMS, which gave us some of the compositions that we needed. So what are tholins? Tholins are really, they're brown. They're like a reddish brownish color. It was coined by Dr. Carl Sagan and Bishon Kerr. And they contain a lot of hydrocarbons. They're typically found really, really up in the atmosphere. And tholins also were found here on early Earth, but they're no longer here, obviously, as time evolved and evolution happened. So they were found, they're typically found on Titan, but they're also really up between the stratosphere, well, a little higher than the stratosphere, but they can be there as well. So why is the haze on Titan important? This helps us understand, again, going back to what I was saying about early Earth, and helping us understand the origins of life and the chemical properties. Now, these chemical properties can also help us understand why is it so thick and hazy there, right? But also where's Titan going in terms of evolution wise? Because right now it's a big mystery. So this is the PHAZER chamber, which we used, and on my left side, as you can see in the purple, this is Titan. Now that it was so, oh my goodness, when I seen this first happen, I was like, oh wow. And so we want to go back to the Miller-Urey experiment, and when we were having those like lightning bolts there, that's exactly what this was doing. And it actually creates tholins. And so if you look closely on the exoplanet experiment, you can see like little dots on them, and those are the tholins. Those were the tholins that were produced in this lab. And so this was the PHAZER chamber. And what I should have told you all in the beginning, if you looked at the picture where I was revealing, not only revealing my height, but when I was leaning on the nitrogen tank, in the back, it was the PHAZER chamber. And so we have a mixture of gas, which can be CO2, methane, and nitrogen. And so these are all input together, giving us a mixture, which then goes to the mass flow controller. And then from that point, we have the pressure gauge and the cooling coil. And so the cooling coil basically mix everything up together, but it then goes to the reaction chamber, which creates the dissociation and ionization as it was in the schematic that I showed you all, which gives us that we have a saying, and it's, we got plasma and things go zap. And so here's the zapping part. And so from this point, it goes from the thermocouple back to the pressure gauge and into the pumps. And then we also have the residual gas analyzer. And so this took about, I want to say it can take anywhere from 24 hours to 3 days. In which obviously there's someone that has to be there and watch this. This is what happens in the lab. And once it's done, we open up the plasma chamber, and as you can see to my left, where you have laboratory made tholins, those tholins that are in the glove box. I was too short to reach the glove box, again revealing my height, but my other lab mates were able to see it for me. I was so hurt. But if you can look around the plasma chamber top, you can look at it, and it kind of looks like the atmosphere of Titan, right? And so from that point, we take some of the tholin, we leave some of them in the glove box. Then from that point, we take some of the tholin and put, as you can see in the middle, we put them in those capsules, and we also lastly, it's ready to get measured. And so we're getting ready to measure it there, which brings us to spectroscopy. And so how does spectroscopy work? Well, spectroscopy is one of my favorite things, and something that I really enjoy learning, taking organic chemistry. but spectroscopy can be understanding the excited molecules in a compound. And so we want to know a little bit more about its groups, its functional groups. And so for those of you that just do not like chemistry, I am so sorry. But it is something that we use to help us understand through absorption and transmission. And that's where the FTIR comes in at. And so we take the tholins and insert them into the FTIR. And so again, we have plasma and got lasers and things go zap in the lab. And so here, it's another part of us zapping things. And so from this point, we insert it into our into the FTIR spectrometer. And once we get the reflection and transmission data from the near infrared and mid infrared, depending on what's happening, we then get these. We then get certain wavelengths and numbers. Now, again, this can only tell us the functional groups. So we, the chemical traces. So like somewhat footprints, if you want to think about them like that. So this does not automatically gives us like, oh my God, it's this molecule. Yes. No, this is only baby steps. So, and as you can see from here, this is the frequency ranges that we got via spectroscopy. And as you can see there, looks like it's some water in there somewhere, which is pretty cool, right? And this is definitely what we ended up with, which I was kind of excited to see, seeing some OH bonds, some CH bonds, which is really cool to understand if you're a chemist. We identified the peaks that were related to the potential functional groups, but this could help to understand more prebiotic chemistry on Titan's surface. And so this was something that was near and dear to my heart for my senior thesis. I worked on it for about 1.5 years, and so I was really excited. And I also worked alongside with Miss Brene Hanat, who was a graduate student in the department. So she and I worked on this project together. And for those of you, I am going to advertise Black in Astro because right now we currently have a scholarship for Black graduate students that want to go to AAS. We will fund you. So we hope to see your face there. We hope to see your face on the website. And you can follow me on Instagram and Twitter, which is _astro_chick. And you can follow all of my other collaborative efforts to help push Black and brown people in and retain them in physics and astronomy and even chemistry. And you can also follow Astrobytes on Twitter. And these are my acknowledgements to Ms. Brene Hanat once again, the Hörst Lab group, Johns Hopkins University, Chicago State University, where I got my bachelor's in chemistry from, and thank you all here at the NAC program. Thank you.
Thank you so much, Ashley. This was such a cool topic. I learned a lot about your favorite moon. Any questions?
Thanks, Antonio. So Ashley, I was just going to say that Pioneer 11, which was oh so long ago, that was actually one of the reasons that I'm an astronomer now, because I thought it was so cool. And I was just going to ask, in terms of priorities for exploration of the solar system, there's a lot of people on the Europa bandwagon as well. So I just wanted to ask sort of what your, I know you said Titan is your favorite moon, but how do you sort of see Titan and Europa, as priorities for exploration?
So I think, isn't Europa Clipper, I believe Europa Clipper is like launching very soon. I think it's going first before. I think it's going even before Dragonfly, if I'm not mistaken. And so, which I'm happy to see. Although, like I love Titan, I also love icy bodies. So I like seeing what's happening with moons in particularly, but I also have an interest in ice giants. So I think you all should just call me Elsa from here on out. I think that'll be cool. I'm just gonna change my name, okay? But I think that it's really cool for us to continuously see things in the solar system. But I am very curious to see what happens with Europa Clipper, and like what findings are there.
So I have a question about the PHAZER chambers.
Mhm.
Is that mimicking the entire atmosphere or like the separate layers? So it's the entire atmosphere.
Yes, it's mimicking the entire. Yes, it's mimicking the entire atmosphere.
Okay.
So, yeah, it's mimicking the entire atmosphere, and that's something that I was also curious about when I first started working on it. But in my other project, don't tell nobody else. It's it's only mimicking the upper atmosphere. So this one is mimicking the whole thing. So
okay.
And we because we really want to know what's happening with its hazes, and that's something that we just can't figure out for the life of us. Like it's literally like a mysterious question, and it's really like Titan's really a jerk. We love it, but it's a jerk because it doesn't let you like peer into and be like, yes, here I'm giving you all the answers to me. No, you have to work for it. So
okay, can I ask a second question? Now that I have that one out of the way. Okay, so out of the PHAZER chambers, you found that it produced these tholins, which you said were also present on early Earth. But from the chemistry point of view, like that's not evidence of life yet. So what else is needed to turn that into life, or, you know, what other kind of signatures from the chemistry perspective would you need to have sort of that smoking gun, like life could be forming here?
Water. And that's, if you notice this right here, which potentially could be water. And so that's what we look at as like, oh, it's habitable. Yay. But but we're not for sure if that is actually there. That could just be like small things there, right? That can just be like just a little droplet, because there is like an ice cap around, like, it's weird. I had the slide up earlier, but I took it down because I was like, I'm not going to confuse y'all. But there's the haze layer, and then there is water around it before you get like into other layers of Titan, and that could be where it's from. So if that makes sense to you, because granted, we have all these other chemicals that could be products of life, because we're also looking at hydrocarbons, amino acids. Those are evidence of life. But most importantly, as we're looking at ocean worlds, typically it's water.
I had one question in regards to the simulation of the spectroscopy. Have y'all been using any other have y'all tried to simulate the spectral features in other simulators?
Besides the PHAZER chamber?
Yes. So like SMART or Atmos.
From the last time I checked, I know they tried to do some stuff with NASA, and then in their chambers, but we'll talk about that later, Leah.
No worries.
But I'll give you the C on that. You're like, what? But I know they did computational modeling, and that was about it. So some of the other folks in the group, they have like different other types of things that they're working on, and some of them did modeling, and that was about it. So basically, this was like our main source of the PHAZER chamber. Oh no, I'm lying. We got the PHAZER chamber. They was using I know Brene used mass spec, and we were using UV. So there were other things that they were using to get these things, but primarily instrumentation.
Gotcha. Would that be something y'all would be considering maybe for your project? So like using like maybe Rocky 3D or something like that?
Right. In the future for my next phase, yes. Definitely yes.
Thank you, Ashley, for coming and give us this amazing talk.